Alright, so I decided for today's pre-lecture video, I wanted to focus on power in a circuit, mostly because it would be something we'd look at towards the end of class, so in case we don't have a lot of time tomorrow, at least you'll all see this material. Alright, so in today's lecture and in the reading, we talked about, or began to talk about, the possibility of current flowing through a circuit. And so here is a very simple circuit that we learn about in this chapter. So we have a battery, and the battery is the source of power. This kind of allows the current to flow. And then we have elements called resistors. And resistors are pieces in the circuit that, as the name suggests, resist the flow of the current through the circuit. Resistors are like an element that you put in a circuit, just like a capacitor would be. And so we'll look at those in a little bit more detail in future chapters. But one of the things that we can think about as we go through the circuit is how the energy sort of ebbs and flows as we go through. So we can imagine a charge going from the negative terminal to the positive terminal in the battery. And again, don't forget from your reading that when we talk about the flow of current, that we think of the current as the way the positive charges would go as they would go around the circuit. Even though it's the electrons that are moving, the convention we use is the way the positive charges would go. But as the charge goes through a potential difference, delta V, it gains potential energy. And remember that that potential energy is going to be equal to Q delta V. But it's also going to lose that energy once it goes through the resistor, because the idea is that the energy that the charge gets, or the current is getting from the battery, is then lost as it completes the circuit. So it'll gain a certain amount of energy through the battery, but once it goes through the last element in the circuit, it will have lost all of the energy that it gained. This ends up making sense because we use the idealization, which we do a lot in physics, that the current or the charges don't encounter any resistance as they go through the wires. It's only these external elements like the resistor. And so it will lose energy, Q delta V, through the resistor. And then the charge can continue back to the battery. And it doesn't need to have any energy to continue through that wire because of the fact, again, that we've supposed that the wire is an ideal wire and it's not going to need any energy to travel through that. Now, another way to look at it is this energy transfer is to think about power. Remember, power is defined as energy per unit time, or the rate at which work is done, or the rate at which energy is gained or dissipated. So if we take the energy that was gained through the battery, remember that was equal to QV. I'm going to use V and delta V interchangeably. Try not to be worried about that. If I want to talk about power, it's going to be QV over time. But Q over time is equal to current, and so this can actually be equal to I times V. And so this is the power that's gained in the battery. As a certain amount of current travels through the battery with some sort of potential difference of V, that's how much power will be gained. You should expect that the same amount of power will be lost through the resistor because the same thing was true about energy. Energy was gained in the battery. Energy will be lost in the resistor. But it might turn out that there might be a more convenient way to express this. First, let's just sort of summarize what we found, is that the power that was delivered to the circuit could be expressed as the potential across the circuit element, which what we were looking at was the battery, and the current that was flowing in the circuit. Now, this might not be as convenient to express for the resistor, but we do have Ohm's law, which we learned in this chapter. Ohm's law says the potential difference is equal to, the current times the resistance. And so what we can do is we can use this to write the power different ways. So for instance, we might want to write, this is similar to when we wrote the energy stored in a capacitor and we use different variables. What if we don't want the voltage to be part of it? We can replace V times I with, the V with I R and then times I, and so we can write I squared R. We could also replace the I term here, so we have V times I, and replace it with V times V over R, and we get V squared R. So different expressions for the power, now we have it three different ways, I times V, or I squared R, or V squared R. These are different ways to write the power that's either gained or lost through an element in our circuit. For instance, the second two, or the last two, might be more useful when we're thinking of a resistor in the circuit, because it does deal with the resistance. And that's one of the things that we could think of. This is how much power is gained when we go through the battery, but this is how much power is lost as we go through the resistor. And so we could look through at this one more time as we go through, as the current goes through this battery, the power, the rated energy is gained is equal to I times V. But then when we go through the resistor, the power that's lost could be expressed as I squared R. So it's related to both the current and the resistance. This is the power that we say is dissipated, it's lost, while this is the power that was gained. We might ask how the power is lost, and one of the ways that we say that is lost is through heat that's given off as the current goes through the resistor. All right, so I hope that this is helpful, just a real short coverage of how we look at power in the circuit. If we get time to do it on Monday, that would be great, but if not, at least we have this to reference.